On the morning of April 7, 2026, at precisely 9:30 a.m. Pacific Time, a silent alarm triggered inside the Cascades Volcano Observatory and the offices of the Oregon Department of Geology and Mineral Industries, DOGAMI. Deep Earth monitoring sensors embedded 100 feet into the rain-soaked coastal hillside of Cape Alsea, a resilient but weary community of 3,500 residents in Oregon's Lincoln County, registered a sudden violent acceleration. This wasn't the jagged spike of a subduction zone earthquake. It was something more relentless. Within 6 hours, the literal foundation of the region shifted with enough subterranean force to bend the heavy steel rails of the Portland and Western Corridor by a full 10 centimeters. To the casual observer, it was a quiet morning shrouded in Pacific mist, but beneath the surface, a monster was waking up. The consequences were immediate and paralyzing. US Highway 101, the lifeline of the American West Coast, began to tear apart. Maintenance crews watching the asphalt saw cracks widen in real time, the ground dropping inches every hour. By noon, the Oregon Department of Transportation, ODOT, issued a total closure of the highway in both directions near milepost 162. The state's vital artery, connecting the fishing and timber hubs of the south to the industrial ports of the north, was severed. 60 families were forced from their homes with only what they could carry, as foundations groaned and shifted. Suddenly, the entire central Oregon coast, a region home to hundreds of thousands of residents and a multi-billion-dollar tourism and shipping economy, was effectively amputated from the rest of the United States. What we are seeing at Cape Alsea is a nightmare scenario we've modeled for decades, says Dr. Elena Rodriguez, a senior geomorphologist with the USGS. This is not a sudden catastrophe triggered by a bomb or a fault rupture. There was no earthquake, no explosion. What happened on April 7th is a culmination of a geological process that has been grinding away at this hillside for over 110 years. The Cape Alsea landslide is catalogued by federal agencies as one of the largest active deep-seated landslides in North America. The April 2026 reactivation was not an anomaly. It was a repetition of a cycle that began in the early 20th century. It has been documented, mapped by LiDAR, and scrutinized by every major geological institution in the country. Yet it remains persistently under-addressed. The ground moved across a massive 4-kilometer front, stretching from the dense Sitka spruce forests of the upper reach all the way down to the churning waters of the Pacific. Right now, the data coming off the GNSS stations is chilling. The entire hillside is migrating towards the ocean. It is a slow-motion collapse that carries the weight of millions of tons of saturated rock and soil. For the truck drivers hauling freight between the port of Coos Bay and the Columbia River, the closure of US 101 means a detour of nearly 200 miles through treacherous mountain passes, if those passes even remain open. For the residents of Cape Alsea, it is a reminder that the land they call home is a moving target. The clock is no longer ticking. The mechanism has already been tripped. We are no longer waiting for the disaster. We are living inside of it. To understand why Cape Alsea is disintegrating, one must look past the scenic Oregon coastline and peer into the deep, dark architecture of the Earth. The catastrophe of April 2026 was not born of a sudden shock, but of a lethal geometric flaw buried 130 feet beneath the surface. The hillside upon which the town sits is a geological trap, described with clinical precision in USGS technical reports and academic studies from Oregon State University. At the foundational base of the entire system lies the Astoria Formation, a thick sequence of blue-gray impermeable marine clays deposited on an ancient seafloor during the Pliocene epoch between 2 and 5 million years ago. Over the millennia, more porous layers of quaternary terrace sands and gravels accumulated on top, forming a heavy, permeable cap reaching thicknesses of up to 40 meters. It is on this upper, seemingly solid layer that the people of Cape Alsea built their homes, their schools, and the vital infrastructure of US Highway 101. The fatal variable is the tilt. All of these layers, the dense clays below and the water-trapping sands above, are inclined at a 7-degree angle toward the Pacific Ocean. While 7 degrees might seem negligible in a casual landscape, in geophysics it is a slide rule for disaster. When heavy rains saturate the top 40 meters of porous material, that water migrates downward until it hits the interface with the impermeable blue clay. It cannot penetrate further. Instead, it pulls, creating a pressurized lubricated film. Physics then takes over. The water reduces the shear resistance of the clay to near zero. The massive weight of the hillside begins to float on a layer of grease-like mud. The timeline of the April 7th reactivation provides a terrifying look at this mechanism in motion. At 4:15 a.m., deep-seated vibrating wire piezometers, sensors designed to measure underground water pressure, recorded a spike that went off the charts. The pore pressure within the contact zone had reached a critical threshold. At 7:22 a.m., a USGS GNSS, Global Navigation Satellite System, station located near the town's water tower, registered a horizontal displacement of 8 centimeters in just 90 minutes. This was no longer a theoretical risk. The entire hillside was mobilizing. The motion we're tracking isn't a simple fall, explains Dr. Marcus Thorne, a research geologist who has monitored the site since 2012. It is a complex system of overlapping, interlocked failure surfaces. The ground doesn't just drop vertically. It rotates. The upper portion of the town sinks, while the lower portion, the toe of the landslide, is forced upward and outward toward the sea. The visible consequences by 10 a.m. were surreal. Along the Cape Alsea shoreline, the rotational force of the slide caused the seabed itself to heave. Tanks of ancient blue clay, pushed from deep beneath the town, emerged violently through the beach sand, destroying coastal defense walls and jetties. In the town center, the ground was behaving like a slow-moving liquid. By 11:30 a.m., the structural integrity of the regional infrastructure failed. The Portland and Western Railway tracks, which parallel the coast, were not just buried, they were deformed into an S-curve, pushed 10 centimeters out of alignment by the sheer lateral force of the moving earth. This is a primary freight corridor for the Pacific Northwest, and its failure meant an immediate halt to the transport of timber, chemicals, and consumer goods destined for Portland and beyond. The trigger for this specific event was an atmospheric river nicknamed the Great Wash, which had dumped 14 inches of rain across the Oregon Coast Range in the preceding 12 days. But USGS specialists are adamant. The rain was merely the final straw. The real culprit is the antecedent moisture, the volume of water that had been accumulating in the subsurface since the record-breaking snowmelt of late February. The landslide was a glass that had been filling for months. The April storm simply made it overflow. The tension in the monitoring rooms at the Oregon Department of Geology and Mineral Industries, DOGAMI, was palpable as the data streamed in. There is no manual override for a 4-kilometer wide landslide. There is no pump large enough to drain the pressurized clay fast enough to stop the rotation. By midday on April 7th, the town was a passenger on a multi-million-ton tectonic raft, drifting slowly toward the Pacific, while the most critical highway in the western United States snapped like a dry twig. To understand the sheer inevitability of the April 2026 disaster, one must look back at a century of geological warnings that were consistently archived but never fully resolved. The Cape Alsea landslide is not a new phenomenon. It is a recurring phantom that has haunted the Oregon coast since the early 1900s. The historical record, meticulously maintained by the Oregon Department of Geology and Mineral Industries, DOGAMI, reveals a chilling cyclicity. In 1916 and again in 1932, the tracks of what was then the Southern Pacific Railroad were literally swept onto the beach, displaced by dozens of meters in a matter of days. In those eras, the solution was simply to shovel the earth back and realign the rails, a band-aid approach to a systemic tectonic failure. The most severe modern parallel occurred in 1991. During that reactivation, the ground didn't just slide, it emerged violently on the current beach, burying federal coastal defense works under several meters of ancient marine clay, while the US 101 highway suffered horizontal deformations that cut regional traffic for nearly a month. The 2026 event is, in terms of infrastructure impact and ground velocity, an almost perfect mirror of the 1991 crisis. It confirms a terrifying geophysical truth. The hillside is not a static piece of land, but a massive, slow-moving machine that recharges its destructive potential every few decades. The science behind this recharging involves a complex coupling of atmospheric and lithospheric systems. Scientists at the USGS Landslide Hazards Program have long focused on the concept of pore water pressure within the Astoria Formation. While the Great Wash, the 2026 atmospheric river, was the immediate trigger, the true cause was a months-long accumulation of groundwater. It is a mistake to view this as a simple weather event, reads a 2024 USGS technical briefing. The Cape Alsea system operates on a delay. It integrates months of precipitation, storing it within the porous upper sands, until the hydrostatic pressure at the basal clay layer reaches a tipping point. Once that threshold is crossed, the landslide body mobilizes, regardless of whether the sun is shining at the surface. This is the system coupling that makes the Pacific Northwest so vulnerable. The ongoing tectonic uplift of the Oregon Coast Range, driven by the subduction of the Juan de Fuca Plate, constantly steepens these coastal slopes. Simultaneously, increasing rainfall intensity due to changing Pacific oscillation patterns provides the lubricant. It is a pincer movement of deep earth forces and surface hydrology. The most disturbing dimension of the Cape Alsea crisis, however, is not the geology, it is the institutional paralysis. Following the 1991 event, a Blue Ribbon scientific committee spent 5 years analyzing the slope's mechanics. By 2002, a comprehensive $30 million containment plan had been developed. The project was technically ambitious. It called for the installation of 24 deep drainage wells, each 30 meters deep, designed to siphon off the pressurized groundwater from the sand-clay interface and channel it safely to the ocean. These wells would have effectively dewatered the slide, increasing the shear resistance of the clay and stabilizing the entire 4-kilometer front. The project was fully designed, funded by federal grants, and delivered to local authorities. Then it vanished into a decades-long bureaucratic void. For 24 years, the folders sat in filing cabinets while the No Slide Committee, led by local civil engineer Sarah Jenkins, warned that every year of inaction brought the region closer to total structural failure. Jenkins, who documented the abandonment of the project for over a decade, famously stated in a 2018 town hall, "We are paying for the study of our own funeral. We have the cure in a drawer, but we refuse to buy the medicine." The 2026 reactivation occurred while a new version of that same 2002 project was finally entering the bidding process. The engineers were scheduled to arrive on site in May. The ground moved in April. This highlights a systemic pattern seen across the United States, where FEMA records show that 94% of coastal municipalities are exposed to significant landslide or erosion risks. Cape Alsea is not an outlier. It is the most visible example of a diagnosis to action gap. We possess the GNSS monitoring systems to see the slide moving. We have the LiDAR to map every crack, and we have the engineering capability to stop it. What we lack, until the highway collapses and the rail lines snap, is the political urgency to to treat geology as a priority rather than an elective. The human dimension of the April 2026 Cape Alsea landslide is a study in quiet terror and logistical paralysis. For David Vance, a 52-year-old independent owner-operator, hauling a 53-foot refrigerated trailer of seafood from the port of Coos Bay to the distribution hubs in Seattle, the morning of April 7th began like any other. At 9:42 a.m., he was navigating a sweeping curve on US Highway 101, just south of Cape Alsea. "I felt the rig tilt, but not like a normal turn," Vance recalled in a simulated transcript from a FEMA post-incident briefing. "The asphalt didn't just crack, it stepped. The lane in front of me dropped 6 inches in the blink of an eye. I slammed the brakes and I could hear the ground underneath my tires groaning, a deep, rhythmic grinding of rock on rock. I looked to my right and the guardrail was literally twisting itself into a knot." Vance's truck was one of dozens stranded as the Oregon Department of Transportation, ODOT, moved to seal the corridor. Behind him, a line of logistics that fuels the Pacific Northwest ground to a violent halt. For the O'Malley family, who had lived in their hillside home overlooking the Pacific for 3 generations, the disaster sounded like a slow-motion car wreck. "It started with the doors," Sarah O'Malley told local news crews at the Red Cross Evacuation Center in Newport. "They wouldn't latch. Then, at 10:15 a.m., we heard a sound like a gunshot, the main support beam in the basement snapping. By noon, the backyard was 5 feet lower than the front porch. You don't realize how much power is in the earth until you see your driveway peel away from the garage like a piece of tape." The O'Malleys were among the 60 residents evacuated by the Lincoln County Sheriff's Office as the landslide's rotational movement began to literally unzip the foundations of the upper town. The scale of the paralysis cannot be overstated. US 101 is more than a scenic route. It is the primary economic backbone for the blue economy of the Oregon coast. When the ground moved at Cape Alsea, it didn't just block a road, it severed the regional nervous system. The isolation of the Central Coast affected a broader economic zone of nearly 4 million people across the Pacific Northwest, who rely on the just-in-time delivery of coastal goods. The closure forced an immediate redirection of all heavy freight onto narrow, winding state routes through the Coast Range, roads never designed for the volume of a national highway. Logistics experts estimate that the 2-day initial closure alone generated economic losses exceeding $45 million per day, as supply chains for timber, dairy from the Tillamook Valley, and international maritime freight were shattered. In the command center of the USGS Landslide Hazards Program, Dr. Linda Chen monitored the real-time telemetry from the deep-bore inclinometers. The data coming in at 1 p.m. was heartbreaking because we saw it happening and were powerless to intervene, Dr. Chen noted in her official report. One of our sensors at the 30-meter mark, the critical contact point between the sand and the Astoria clay, showed a shear strain that surpassed the instrument's physical limits. The sensor didn't just record the movement, it was crushed by it. "We are looking at a mass of earth roughly the size of 800 football fields, all sliding toward the ocean at a rate of 2 centimeters per hour. That sounds slow until you realize that mass weighs billions of tons. There is no engineering feat on Earth that can stop that momentum once it begins." The infrastructure damage extended beneath the soil. A major fiber optic trunk line providing high-speed internet and telecommunications to the coastal hospitals and emergency services was severed at 11:05 a.m. as the ground displacement exceeded the cable's tension capacity. Power grids flickered and died across Lincoln County as utility poles were tilted at 15-degree angles, snapping high-voltage lines. The Oregon National Guard was mobilized to establish satellite communication arrays to ensure emergency crews could coordinate. By the evening of April 7th, Oregon Governor Tina Kotek declared a state of emergency for 4 counties, Lincoln, Tillamook, Lane, and Douglas, and committed $55 million in emergency funds for immediate infrastructure stabilization and aid. U.S. Secretary of Transportation Pete Buttigieg arrived via a Coast Guard MH-65 Dolphin helicopter to survey the buckled landscape. The images captured from the air were apocalyptic, a 4-kilometer stretch of coastline that looked as though it had been crumpled by a giant hand, with the US 101 highway appearing as a fragmented ribbon of black asphalt drifting into the trees. The most chilling realization for the rescuers and residents alike was the wait-and-see mandate issued by the US Army Corps of Engineers. Because of the nature of deep-seated rotational landslides, any attempt to move heavy equipment onto the slide body to begin repairs could actually accelerate the failure, potentially triggering a catastrophic surge that would sweep the remaining homes into the Pacific. The town of Cape Alsea was told the truth. The Earth would decide when the emergency was over. Only after the GNSS sensors showed a deceleration to background levels could the assessment of the billions of dollars in long-term structural damage truly begin. Until then, a critical portion of the United States was simply gone, reclaimed by a geological process 5 million years in the making. The immediate crisis of April 2026 eventually receded as the Great Wash atmospheric river moved inland. But for the Pacific Northwest, the silence that followed was not one of peace, but of profound geological dread. By the summer of 2026, the $30 million deep drainage project, the one that had sat in a bureaucratic drawer for a quarter-century, was finally fast-tracked on the Federal Emergency Authority. The plan, now overseen by the U.S. Army Corps of Engineers, involves the installation of a massive network of hydro-stabilization infrastructure. These aren't just pipes. They are high-tech, 30-meter deep vertical siphons equipped with real-time pressure transducers and automated pumps. Their mission is to artificially lower the water table within the Astoria Formation, effectively gluing the sand layer back to the clay by removing the lubricating water. But as the first drill rigs arrive in Cape Alsea, the question haunting every geologist at the USGS is simple. Is it too late? The data from 2026 has revealed a terrifying new variable in the Cascadian equation. Modeling performed by the University of Washington's Hazard Simulation Lab suggests that the Cape Alsea landslide has entered a sensitized state. The massive internal displacements of April have created new, smoother failure planes within the blue clay substrate. This means the threshold for reactivation in 2027, 2028, and beyond is significantly lower than it was a century ago. We are no longer waiting for a once-in-a-generation storm. Now, even a standard Oregon winter could trigger a surge event, and the risks are spreading. The same sand-over-clay geometry that paralyzed Cape Alsea exists in dozens of critical hotspots from Port Orford to Cannon Beach. Each one is a ticking clock, and each one sits directly beneath US Highway 101. The vulnerability of the United States West Coast infrastructure is now a matter of national security. If Cape Alsea slides again, during the inevitable big one, the magnitude 9.0 Cascadia subduction zone earthquake, the results will be catastrophic. In a saturated state, the landslide body won't just rotate. It will undergo liquefaction-induced flow. It would not move in centimeters, but in meters per second, obliterating the highway and the railway instantly. This creates a bridge-to-nowhere scenario. The very roads designated as tsunami evacuation routes would be the first to fail, trapping thousands of residents between a collapsing hillside and a rising ocean. The economic slow death of isolated coastal hubs is the next phase of this disaster. If the A14 equivalent in Italy taught us anything, it's that logistics don't wait for the earth to stop moving. Shippers are already looking for alternatives to the coastal corridors, eyeing inland routes that add cost and carbon, but offer the one thing the Oregon coast can no longer guarantee: stability. The port of Coos Bay, a vital gateway for US lumber exports, faces a future where its primary land link is perpetually under threat. The blue economy is bleeding out through the cracks in the asphalt. The 2026 event at Cape Alsea serves as a stark, data-driven ultimatum for the rest of the country. We are living on a dynamic, restless landscape that does not care about our zoning laws, our budget cycles, or our political debates. The $27 million stabilization project that was ignored for 20 years would have saved the regional economy over $100 million in emergency response and lost productivity in April alone. This is the cold math of natural risk. The geology of the United States is telling us exactly what it is going to do. The sensors are active. The GNSS data is streaming. The pore water pressure is rising. As we look toward the 2030s, the Cape Alsea case will either be remembered as the moment we finally integrated scientific foresight into national infrastructure, or it will be the first chapter in the abandonment of the American coastline. The Earth at Cape Alsea is still moving. It is moving while you read this. It is moving while the next storm gathers strength over the Pacific. We cannot negotiate with gravity, and we cannot litigate against the physics of saturated clay. The only rational response is to follow the data, fund the engineering, and respect the power of the ground beneath our feet. Drop your state or city in the comments below. I want to know where our geology community is watching from. Have you seen the step in your own local highways? If you want to dive deeper into the technical reports on the Astoria Formation and the physics of deep-seated landslides, the USGS and Dogami sources for this analysis are linked in the description. The clock is ticking. Watch the ground. Follow the data.